In our own galactic neighborhood, researchers have made an astounding discovery of the universe's most ancient stars. Greetings, everyone. Today's video focuses on a fascinating discovery made by researchers. They have recently unearthed the oldest stars in the universe, known as SAS stars, within the outer region of our very own Milky Way galaxy. These remarkable stars took shape a staggering 12 to 13 billion years ago and are thought to have originated from smaller primitive galaxies that were assimilated by our own. Through a meticulous analysis of their chemical makeup and orbital patterns, the team was able to pinpoint these ancient stars and hopes to uncover even more in order to gain insights into the evolution of ultra-faint dwarf galaxies. So, without any further delay, let us dive right into our discussion. In the vast expanse of the Milky Way's halo, a cluster of stars caught the attention of the team. This celestial cloud, encompassing the entirety of the galactic disk, revealed three stars that came into existence approximately 12 to 13 billion years ago, coinciding with the emergence of the earliest galaxies. The team of researchers has bestowed the name SAS upon these celestial bodies, an acronym representing small accreted stellar system stars. Their hypothesis suggests that each star was once a part of an individual rudimentary galaxy that was subsequently assimilated by the expanding Milky Way. These three stars now stand as the sole remnants of their original galaxies, orbiting the periphery of our Milky Way. The team postulates that there may exist additional ancient stellar survivors in this region. MIT professor of physics Anna Friebel affirms that these ancient stars are undoubtedly present, based on our understanding of how galaxies are formed. These stars hold a significant place in our cosmic lineage, and we have now discovered a novel method to locate them. In their quest to discover comparable SAS stars, the scientists are optimistic about utilizing them as substitutes for ultra-faint dwarf galaxies, which are believed to be among the earliest galaxies in existence. These galaxies, although still in existence, are located too far away and emit too little light for astronomers to thoroughly investigate. Given that SAS stars may have originated from primitive dwarf galaxies similar to those, but are now present in the Milky Way and therefore much nearer, they could serve as a valuable resource for comprehending the development of ultra-faint dwarf galaxies. According to Friebel, the discovery of brighter analogues in the Milky Way allows for a more convenient study of their chemical evolution, eliminating the need to pursue these exceptionally dim stars. The results of their research have been published today in the monthly notices of the Royal Astronomical Society, MRAs, by her and her colleagues. The co-authors of the study include Mohammed Mardini from Zaka University in Jordan, Hilary Andales, 23, as well as current MIT undergraduates Ananda Santos and Casey Feenberg. The team's remarkable findings were born out of an educational concept. During the fall semester of 2022, Friebel introduced a new course called 8, S30, Observational Stellar Archaeology, where students were taught techniques for analyzing ancient stars. These techniques were then applied to previously unexplored stars in order to uncover their origins. According to Andales, unlike the majority of our classes that start from the basics, this particular class immediately immersed us in the forefront of astrophysics research. Using star data gathered by Friebel over several years from the 6.5-meter Magellan Clay telescope at the Las Campanas Observatory, the students delved into a thorough examination of the information. Stored in a substantial binder within Friebel's office, hard copies of the data were meticulously scrutinized by the students in search of noteworthy stars. The focus of their search was primarily on ancient stars that originated shortly after the Big Bang, an event that transpired approximately 13.8 billion years ago. During this period, the universe consisted predominantly of hydrogen and helium, with minimal quantities of other elements like strontium and barium. To identify these stars, the students meticulously examined Friebel's collection, specifically targeting stars with spectra that exhibited diminished levels of strontium and barium. The focus of their investigation honed in on three stars that were initially detected by the Magellan telescope during the years 2013 and 2014. These specific stars had never been further examined by astronomers to analyze their spectral characteristics and determine their source. Consequently, they presented ideal opportunities for the students in Frebel's class. In order to properly analyze the spectra of 3 stars, the students were taught the process of characterizing a star. By utilizing different stellar models, they successfully identified the chemical composition of each star. It was discovered that the intensity of certain features in the stellar spectrum, which align with specific wavelengths of light, directly correlates to the abundance of particular elements. Upon completing their examination, the students reached a firm and assured determination that the trio of stars did indeed possess remarkably diminished levels of strontium, barium, and various other elements, including iron, in comparison to our own Sun, which served as the point of reference. Remarkably, one of the stars contained a quantity of iron to helium that was less than 1/10,000th of what is found in the Sun at present. Recalling the arduous process of solving the puzzle, Santos reflects on the countless hours spent fixated on a computer screen, troubleshooting and exchanging frantic messages. It was a steep learning curve, but an extraordinary journey nonetheless. The star's scarcity of chemicals suggested an ancient origin dating back 12 to 13 billion years. Remarkably, their chemical composition closely resembled that of ancient, barely visible dwarf galaxies, as observed by astronomers in the past. Could it be possible that these stars emerged from similar galaxies? And how did they find their way into the vast expanse of the Milky Way? Taking a spontaneous intuition into consideration, the researchers examined the celestial bodies' trajectories and their motion across the expanse of the heavens. These 3 stars are dispersed across various regions within the vast halo of the Milky Way and are approximated to be situated approximately 30,000 light-years away from our planet. To provide context, the diameter of the Milky Way's disk spans a distance of 100,000 light-years. During their analysis of the star's orbits around the galactic center, utilizing data collected by the Gaia astrometric satellite, the researchers made an intriguing discovery. In contrast to the majority of stars in the main disk, which follow a predictable trajectory akin to cars on a racetrack, all 3 of these stars exhibited an unusual behavior. They were moving in the opposite direction. This phenomenon, commonly referred to as retrograde motion in the field of astronomy, indicates that these stars were likely acquired from external sources through a process known as accretion. According to Frebel, the occurrence of stars moving in a different direction from the rest of the group can only be explained by the possibility of them being thrown in the wrong direction. The unique orbital patterns and distinct chemical compositions of these 3 stars, which differed from the rest of the galactic disk and halo, provided compelling evidence for their ancient origins and affiliation with older dwarf galaxies that had merged into the Milky Way at various angles, persisting in their trajectories billions of years later. Intrigued by the possibility of retrograde motion in other ancient stars within the previously analyzed halo, Frebel conducted a thorough examination of scientific literature. To her surprise, she discovered an additional 65 stars with low strontium and barium abundances that seemed to exhibit the same defiance against the galactic flow. Surprisingly, all of them are exceptionally swift, moving at speeds of hundreds of kilometers per second, but in the opposite direction, Frebel remarks. They're fleeing. The reason behind this phenomenon remains unknown, but it provided the missing element to our puzzle, one that I hadn't anticipated at the outset. With great enthusiasm, the team is determined to explore additional ancient SAS stars. To accomplish this, they have devised a straightforward procedure. Initially, they will identify stars with minimal chemical elements and subsequently monitor their orbital paths for indications of retrograde movement. Out of the vast expanse of over 400 billion stars within the Milky Way, they anticipate that this approach will reveal a noteworthy quantity of the universe's most ancient stars. With admiration and gratitude, Frebel intends to relaunch the class this upcoming fall, reflecting on the initial course and the 3 students who successfully published their results. Working alongside 3 female undergraduate students has been an incredible experience. This is something I have never had the opportunity to do before, and it truly exemplifies the values and ethos of MIT. We believe in taking action and providing equal opportunities for everyone who expresses a desire to be involved. When individuals are given the chance to participate, remarkable things can occur. The National Science Foundation played a partial role in providing support for this research endeavour. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.